Hello everyone, myself Dr. B.S. Ganesh from the EEE department. Now I am going to explain basics of electrical machines. In this we have different types of basics, and first and foremost basic is Oersted principle. So first basic is Oersted principle. According to this Oersted principle, see, this Oersted principle says that every current carrying conductor will produce magnetic flux. Every current carrying conductor will produce magnetic flux. That means, for suppose if we connect, this is my conductor, let us say AB. AB is one conductor. I am connecting AB to the one battery. Then what will happen? Current is flowing through this conductor. So current is flowing through this conductor from high potential to low potential. So this is our current. Now according to Oersted principle, every current carrying conductor produce its magnetic field. That means the magnetic field is produced around this conductor. This is given by the Oersted. Now we know that every current carrying conductor will produce magnetic flux according to the Oersted principle, but we don't know the what is the direction of this magnetic flux. To find this direction of the magnetic flux, again we have two things. One is, if the current carrying conductor is a straight conductor, and if the current carrying conductor is a coil. We have both two types of cases. So in first case, that is, this is the current carrying conductor. So here this is the current carrying conductor, and this is the current carrying coil. This is current carrying coil. So in this case, how to find the direction? So by using right hand thumb rule, we can find the magnetic flux direction in current carrying conductor as well as the current carrying coil. So how to find this by using right hand thumb rule? That means just to hold this conductor, that is suppose this is the conductor and current is flowing in this direction. Just if you hold this conductor like this, then this thumb indicates the current direction, and this wrapped finger indicates the flux direction. So for suppose the current is flowing in this direction, if you hold this, this is the thumb indicates means current direction, and wrapped finger indicates the flux direction. So our flux direction is like this. So we can say by using right hand thumb rule, the flux direction is like this. For suppose if it is a coil, our thumb indicates the flux direction and current indicates the wrapped finger indicates the current direction. So here these are the wrapped fingers. So thumb indicates the flux direction. That means here the flux is coming out from the coil. For suppose here flux is out from the coil, the flux must be enter here. So this will close the path like this. Again here we have one more basic. So this is by right hand thumb rule. This is by Oersted principle. Again here we have one more basic, that is, so here the flux direction is like this. For suppose if you consider a bar magnet, so this is our north pole and this is our south pole. So in every bar magnet, the flux direction is leaving the north pole and outside the magnet leaving the north pole. That means the flux is like this, and here the flux is like this. Outside the magnet, the flux is leaving the north pole and enters the south pole. Inside the magnet, the direction is south to north. Inside the magnet, south to north. Okay. Outside the magnet, north to south. Inside the magnet, south to north. Now, if you compare this magnet and this magnet, whenever the flux is leaving the magnetic material, that is north pole. Whenever the flux is entering to the magnetic material, that means or leaving the air gap, or here entering the air gap, or entering the air gap. So whenever the flux is entering to the air gap, that is north pole. Whenever the flux is entering to the magnetic material, that is south pole. So now this pole is south pole because the flux is entering to the magnetic material. Actually here we are taking air core. If you place a magnetic material here, so whatever it may be iron piece or silicon steel or whatever it may be. So if you place a magnetic material, so whenever the flux is entering to the magnetic material, that is south pole. Whenever the flux is leaving the magnetic material, that is north pole. So by comparing these two, we can say this is north pole and this is south pole. Now again hold this coil with our right hand like this. That is, the wrapped finger indicates the current direction and thumb indicates the flux direction. Now our thumb indicates the north pole. Our thumb indicates the north pole. According to right hand thumb rule, our thumb indicates the, here the thumb indicates the north pole. So whenever we want to find out the direction of magnetic flux, by using right hand thumb rule, so our thumb indicates the north pole. Now coming to, so these are the these are the three basic rules. One is Oersted principle, next one is the right hand thumb rule, and next one is the finding the flux direction of magnetic coil by using a bar magnet. Now coming to one more basic, that is Fleming's Now coming to next basic point, that is Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. Again, these are two types. One is Faraday's first law. So this is the first one is Faraday's first law. And second one is the Faraday's second law. Second one is the Faraday's second law. Okay. Now coming to what is Faraday's first law. So according to Faraday's first law says that if a conductor cuts the magnetic flux, then EMF is induced in the conductor. That was given by the Faraday's first law. So that means, for suppose if you consider a north pole here and if you consider south pole here, flux is always flowing from north pole to south pole outside the magnet. So the flux is always flowing from north to south pole outside the magnet. Now just take one conductor and place here. Take one conductor and place here. Okay, so I'm taking one conductor, I'm placing here, and if you shake this one, okay, or if you move this one, or if you rotate this one, what will happen? EMF is induced in this conductor. EMF is induced in this conductor, and if you provide closed path, then current will flows. Okay, understood? EMF is induced without closed path. Okay, just if you shake this conductor or if you rotate this conductor inside the magnetic flux, then what will happen? EMF is induced in this conductor. If you provide closed path, then only current will flows. Otherwise, only EMF is induced. That is given by the Faraday's first law. Okay, so here again here Faraday's first law. Okay, now EMF is induced. This EMF induced direction can be found out by Fleming's right hand rule. Fleming's right hand rule. Okay, so that is we can say it is a dynamically induced EMF. That means here the flux is constant but conductor is varying. Flux is constant, conductor is varying, so it is dynamically induced EMF. For dynamically induced EMF, we are finding this produced EMF direction, so we are using Fleming's right hand rule. So by using Fleming's right hand rule, that means just consider a Fleming's right hand rule. So this is the right hand. All the these three fingers are perpendicular mutually each other. So here the thumb indicates the motion of the conductor, and forefinger indicates the flux direction. Thumb indicates the motion of the conductor, forefinger indicates the flux direction. Now coming to this middle finger indicates the current direction. So if you consider all fingers like this, mutually perpendicular to each other. For suppose if it is a thumb, then it will indicate the motion of the conductor or direction of rotation, and here the forefinger indicates the flux direction. Forefinger indicates the flux direction, and here middle finger indicates the current direction or EMF direction. current direction or EMF direction. That is by using Faraday's first law. So Faraday's first law is, what is Faraday's first law says? So if you rotate the conductor in magnetic flux, then EMF is induced by this EMF direction can be found by Fleming's right hand rule, and the magnitude of dynamically induced EMF is given by flux cutting rule. Magnitude of induced EMF is given by flux cutting rule. That formula is E is equal to V cross B into L. Units are volt. Here V cross is nothing but linear velocity. This V cross is nothing but linear velocity, and here B cross is nothing but flux density. This is flux density, linear velocity, flux density. And here L is nothing but active length of the conductor. This is very, very important. Active length of the conductor. So what is meant by active length? For suppose if you consider this is the conductor, and here the length is the conductor is AB. From here to here, this is conductor is rotating inside the magnetic flux, but the conductor lying in the magnetic flux is this one. That is the length of the wire lying in the magnetic flux is this one. This is called the active length. This is called the active length. So we can say it is the length of the wire in which the length of the wire magnetic field produced, EMF is induced or torque will produce or energy conversion will take place is called the active length. So from here to here, this is only active length of the conductor, and the direction is given by Fleming's right hand rule, and the magnitude of induced EMF is given by flux cutting rule for dynamically induced EMF, that is V cross B into L. So we can say it is, we can say that is, we can write it as VBL sin theta. VBL sin theta. Here theta will give us the angle between linear velocity and magnetic flux density. So both are in volt. Both are in volt. Next one, statically induced EMF. So for the example of dynamically induced EMF is all the generators, whether it is a DC generator or AC generator. For both the generators, the induced EMF is dynamically induced EMF. Why? Because here one of the part is moving, that is either field is moving or conductor is moving. So this we can call it as a dynamically induced EMF. Now coming to statically induced EMF. Statically induced EMF. In statically induced EMF, there is no motion between conductor and flux. Okay, only here the relative motion is existing between conductor and flux is statically. That means if the time varying flux cuts the conductor, then EMF is induced in the conductor. So for suppose this is my time varying flux, that is sinusoidally varying. So if I place a conductor inside the sinusoidal flux, then the flux is cutting here. So here I am giving just analogy, but this is not an accurate picture. So this is I am giving just analogy. So here I am placing conductor, this is statical, and here this is varying with respect to time, not spatially varying. This is with respect to varying. So if you connect external load, then what will happen? Here EMF is induced, then if you connect external load, current will flowing. Okay, this is AC in nature. So the statically induced EMF, or the example for statically induced EMF is transformer. So in transformer, what will happen? The induced EMF, that is from the primary to secondary, how it will happen? So here there is no rotating part, just simply cutting the flux from the primary to secondary side, then EMF is induced on the secondary side. So this is the transformer action. So this is called the statically induced EMF. The statically induced EMF direction is given by the Lenz's law. Statically induced EMF direction is given by the Lenz's law. So according to Lenz's law, effect will oppose the cause. Effect will oppose the cause. So we can write it as a E is equal to minus N d phi by dt. N d phi by dt. So here the minus indicates the direction. So this direction is given by the Lenz's law. Here effect opposes the cause. Here the effect is induced EMF. Cause to produce EMF in this conductor is change in flux. Okay, change in flux, that is time varying flux. So induced EMF is equal to minus n d phi by dt. So here the minus will gives us the direction. Okay, so here minus will gives us the direction that is given by the Lenz's law, and the magnitude is given by the Faraday's second law. So Faraday's second law. So what is Faraday's second law? So according to Faraday's second law, the statically induced EMF in the conductor is directly proportional to rate of change of flux linkage. Rate of change of flux linkage, or we can call it as a rate of change of flux. So simply sometimes we are taking psi is equal to n phi, so we can write it as E is equal to minus n d phi by dt. So according to Faraday's second law, so what we can say, so according to Faraday's second law, the induced EMF in the conductor, that is statically induced EMF in the conductor, is directly proportional to rate of change of flux linkage or rate of change of flux, and the direction is given by the Lenz's law, that is E is equal to minus n d phi by dt. So these are the Faraday's laws of electromagnetic induction. And here we have one more important basic concept is there, that is how to find the direction of current in the conductor. That means, for suppose if you observe this arrow, and if you stand here, okay, so if you observe this arrow, if you stand here, what you are observing? Here we are observing only tip of the arrow. This tip of the arrow means, for suppose if it is a conductor, tip of the arrow means only dot. Okay, that means if the current is towards to the observer, that means arrow is towards to the observer, then what we are finding here? Dot only. So we can call it as a dot. And if the current is, for suppose if you stand here, and if you observe the arrow, what we are seeing from here, we can see shape V, that is arrow shape V. That means if the current is away from the observer, we can say it is a cross. So here it is dot, that is current is towards to the observer, it is dot, and if current is moving away from the observer, then it is cross. So by simply we can get it from the arrow. This is the one more important basic point. And for suppose if you want to find out the magnetic flux around this conductor, that means here this is the conductor and it is carrying cross. That means the current is away from the observer, means current is inside the board. And how to find the magnetic flux? Again by using Fleming's right hand rule. So according to Fleming's right hand rule, thumb indicates the current direction, wrapped finger indicates the flux direction. So here current is away from the observer, that is inside the board, so you can place here. And this wrapped finger indicates the flux direction. So the flux direction around this conductor is clockwise direction. So flux will produce like this by cross conductor, that is current away from the observer. Now similarly if you observe this dot conductor, this is our dot conductor. Now how to find the direction? By using Fleming's right hand thumb rule. So right hand thumb rule means here the current is outwards the board, that means current is towards to the observer, so the thumb indicates towards to the observer current direction, so we can place like this. That means current is towards to the observer or out from the board, so we can place like this. Then this wrapped finger indicates the flux direction, so the flux direction is counterclockwise direction. The flux direction is counterclockwise direction given by the dot conductor on the plane. Okay, these are the most important basic points for to study any electrical machine, whether it is a generator, motor, transformer, induction machine, whatever it may be. Now coming to different types of induction machines. Now coming to different types of electrical machines. So electrical machines basically classified into two types. One is a DC machine and second one is the AC machine. This is DC machine and AC machine. Again AC machines are two types. One is generator and another one is the motor. So in this two machines we are mostly preferable DC generator. Now coming to AC machine. Here we have three types of machines. One is synchronous generator or alternators, and second one is the induction machines or motors, Again here we have a synchronous motors also, and here one more important device is there, that is transformer. Okay, so these are the basic types of electrical machines. For all these machines we are using similar basics. Now we will discuss the first start from the AC generator, basic AC generator, how it will produce the AC in AC generator. Okay, this is the AC generator diagrams. So every generator AC generator, most of the generator in general generators are rotates in clockwise direction. Generators are rotates in clockwise direction. In general, motors are rotates in counterclockwise direction. So here I am considering clockwise direction. Here I am considering a basic two conductors, sorry, one turn coil inside the north pole and south pole. These are the split rings. In general, AC generator we can call it as a split ring generator, or we are using split rings in the AC generator. Okay, split rings plus brushes arrangement. So this is my brush B1. Let us take this is brush B2. So here initially the conductors are, this is my flux direction. Okay, initially my conductor is in this position. Okay, that means there is no flux linkage. Sorry, flux linkage is maximum for the conductor and flux cutting is 0 for the two conductors. So here the flux cutting is 0. Flux cutting is 0. Flux linkage is maximum. If the flux linkage is maximum, flux cutting is 0, then EMF is equal to 0. EMF is equal to 0. Then I am rotating this conductor, some moving, some push. So here this is my conductor's alignment, that is maximum flux cutting and 0 flux linkage. So if you observe here, the flux is flowing from north to south. Okay, this is my flux direction, and this is the generator is rotating in clockwise direction. Generator is rotating in clockwise direction. Same conductors I am representing here. So here this is the AB conductor. So AB conductor is rotating in clockwise direction. So that means conductor is rotating in this direction, clockwise direction. Whatever the flux direction? Flux direction is from north to south. Again, if you want to find out the direction of current in the AB conductor, so we need to use right hand thumb rule, because here this is the generator. So to find the direction of induced EMF in the generator, we are using Fleming's right hand rule. So according to Fleming's right hand rule, thumb indicates the motion of the conductor. Here the motion is upwards, that means clockwise direction. So we can say it is a upward direction. Then here the forefinger indicates the flux direction. So here the flux is from north to south. So here flux is from north to south. This is forefinger and this is the thumb indicates. Then again, so whatever the direction of induced EMF, it is inside the board. This is inside the board, means away from the observer. So we can say it as a cross. We can say it is a cross. So how it will flows the current? So from the A to B, current will flow like this. Here the current will flow like this. Here the current will flow like this. Now coming to CD conductor, again apply right hand thumb rule. Sorry, again apply Fleming's right hand rule. So here the motion is downwards. Why? Because it is moving in clockwise direction. So it is always moving in clockwise direction. So motion is in downwards, and the flux direction is north to south. Then so if you observe this one, so current is towards to the observer. The current is towards to the observer means it is dot. So we can say it is a dot. So dot means here current is moving towards to the observer. Here this is the brush B1 and this is brush B2. So current is moving in this direction. So in passive element, whenever the current enters the passive element, we can take it as a positive. Whenever the current is leaving the passive element, we can take it as a negative. So here this is my current direction. After 180 degrees rotation, here this is my conductor. After 180 degrees rotation, These are my conductor alignments. So after 180 degrees rotation, what will happen? The conductor lying on the north pole comes to the south pole, that is AB comes to the south pole. The conductor lying on the south pole side comes to the north pole because it is rotating. So after 180 degrees rotation, what will happen? So conductors are lying is like this. Conductors are lying in this fashion. Now again observe the current direction in CD as well as the AB conductor. Again here the flux is flowing from north to south. So this one is the flux direction. Again apply Fleming's right hand rule, and the motion of the conductor is clockwise because the generator is in general rotating in the clockwise direction. So it is upwards. Now if you observe the direction of current in the CD is dot. Okay, this is away from the observer. Now if you observe the current direction, so current is away from the observer means it is going like this. This is the dot. Sorry, this is cross. Current is away from the observer means cross. Now coming to conductor AB. Now the motion of the conductor is downwards. Why? Because the generator is rotating in clockwise direction. So here the thumb indicates motion of the conductor and forefinger indicates the flux direction. Now the current direction is towards to the observer. Towards to the observer means this is dot. So here dot means towards to the observer. Current is like this. Now let us take this is brush B1 and this is the brush B2. Current is coming in this direction. So whenever the current, so these are the directions of the conductor. Here I draw a small mistake. Here one more thing. Here the current conductor AB always connected to the brush B1. Here conductor AB always connected to the brush B1. So here the conductor AB always connected to the brush B1 because these are the slip rings, not split rings. So conductor AB always connected to the brush B1 and conductor CD always connected to the brush B2. So this is B1, this is B2. Now if you observe the current direction, so here the current is coming in this direction. Now current is coming in this direction. So here the current is flowing here and here the current is flowing. So this is our current direction. This is our current direction. Now whenever the current is entered into the passive element, that is positive, and here the current is leaving the passive element, that is negative. Now if you observe these two cases, here here the current is for suppose let us take this is M and L load we are considering, this is L and this is M. L and M. Now if you observe both the cases, in previous case at L we are observing minus, that is negative, and now the case is after rotation of 180 degrees at L the current is entering at the passive element, that is positive. Here it is negative and here it is positive, and compared to previous case at point M it is positive and it is negative. That means in load the current is always AC if you use split rings. Now coming to the armature side, that means in turns, that is in conductors, what will happen? Previously that is in case 1 the conductor is lying on the north pole. Here current is away from the observer, that is cross. After 180 degrees rotation current is towards to the observer, that is dot. So here also the current is changing the direction. First it is cross and after this one dot. That means current is changing, so it is alternating in nature. Again if you observe the conductor CD, so here previously it is dot, now it is cross. This is the cross. So we can say in any generator armature will produce alternating quantity, but if you consider whether it is a split rings or slip rings, the output will changes. If we use split rings, then the output is also alternating in nature. So this is AC in nature by using split rings plus brushes arrangement. And one more point we can observe here, the conductor under the north pole is always producing cross in general, and conductor under south pole is producing always dot without changing the direction of rotation. And here if you observe this one, the current carrying conductor under the north pole is always cross and in general, and here the current carrying conductor in under the south pole is dot. So this is about the AC generator. Then we will discuss about the DC generator. So this is the discussion regarding the AC generator, that is split rings plus brushes. Then we will discuss the DC generator in the next video.